Hey everyone, Mr. Fransky back here to talk to you about 8.7, which is about infinite series. You may notice that we skipped 8.6. 8.6 is a lot about taking out loans and mortgages and interest rates and that kind of stuff. And we're going to focus on kind of more the nuts and bolts of looking at these infinite series and not concern ourselves so much with the financial side of things. You do that a lot in advanced algebra, and you also do it a lot in pre-calc, so I'll spare you in FST. So let's take a look at what they're talking about with this whole idea of infinite series. So what is an infinite series, first of all? Well, we've talked about finite series so far. So finite series, remember a finite series is Sn. So Sn means I want to add up the first n terms of the series. So that's what we call a finite. That's what we call a finite series. So an infinite series is one where we don't stop. We just keep adding the terms up. So if you want to write this down in your notebook, in general, an infinite series is an indicated sum that can be expressed in this form. So we're summing from 1 all the way up to infinity. So we do a1 plus a2 plus a3 plus a4 plus a5 plus a6. And we never stop. We just keep adding those terms up together just over and over again. Now at first, you intuitively might think that if I keep adding numbers together, isn't that just going to get big and turn out into infinity? And the answer is most of the time, yes. But the interesting ones are the ones where you can actually add an infinite number of things together and you end up with a finite number, which is kind of cool. So the way that we define this, the way that we can actually look for series like this that converge, even though you're adding an infinite number of things, we start by looking at what we call partial sums. So these are called partial sums. Partial sums. So each one of these here is a sum of a certain number of terms. So the first one is just the first series is just the first term. The second series is going to be the sum of the first two terms. The third series is the sum of the first three. So we're just looking at those finite series that we were talking about earlier this week. So if I keep looking at that, I say, okay, well then the nth series will have the first n terms. And I can keep doing this. And what actually happens here is I create a sequence of its own. So S1, S2, S3, all the way up to Sn, these create a sequence themselves. And what we can do is look at all those numbers and see if it looks like they're converging to some number. So we see what's happening as n gets very large. In fact, we might even say we're looking at the limit as n approaches infinity of these series. Are they approaching some number, or are they getting ridiculously big, or are they getting ridiculously small? So what we say here is we call this S infinity. So the limit as n approaches infinity is called S infinity. This is all right down here. So S infinity is just the sum from 1 to infinity of the terms of our sequence. So we call it a series when we add them all together, but we're adding all the terms of the sequence together. Another way to write that is just we're looking at the limit as n approaches infinity of our finite sums. And that's the same as the limit as n approaches infinity of the sum from 1 to n of ai. So this just means if we look at the sum of the first n terms, but then we make n bigger and bigger and bigger and bigger. So we keep making n as large as we can. What's happening to the sum of these terms? And again, intuitively at first you think, I'm adding a whole lot of things together. Shouldn't that just go to infinity? Is there any way that that's going to end up leveling off at a term? And it's interesting that there actually are some that do that. So here is a visual idea of an infinite series. So this is like just looking at the integers. So if we consider the arithmetic sequence 1, 2, 3, 4, 5, etc., etc. So we're just looking at all of the natural numbers. We start at 1 and we keep going up. If we add these all together, 1 plus 2 plus 3 plus 4 plus 5, and we keep adding to infinity, I think it's pretty obvious that this is going to end up being way big. I mean, it's going to be infinity like multiple times over because we keep adding these really big numbers together once we get off to big n values. And we see that with these blocks here. All right, so if we add all these blocks together, we start with just one block, then we have 3 blocks, then we have 6 blocks, then we have 10 blocks. If you were to keep adding these together, you're going to get numbers very big very quickly. So this is something worth noting, is that arithmetic sequences, or arithmetic series we could say, arithmetic infinite series always diverge. They always diverge. The only exception is if you're looking at the really not very interesting sequence where an equals 0 for every single n in the series. Because if it's always 0, you're just adding a whole lot of zeros together, which means it converges to 0. Otherwise, arithmetic infinite series are always going to diverge. Whether you're adding or you're subtracting, it doesn't matter. They're always going to diverge. I don't think I have anything else on this slide. So, will it always be divergent? Well, I keep kind of alluding to this idea that, no, there are some that are going to converge. And let's take a look at one of those. So this is one we've talked about a little bit before, and has already gotten a few people upset because they keep saying, I just don't understand how you can add all these numbers together and say that they actually equal a number. Well, let's take a look at this visually and see if it makes a little bit more sense. So look at these three diagrams. The shaded regions here are representing the sum, Sn, so these are finite sums, of the first n terms of this infinite geometric series. So we are looking at the sequence with the terms 1/2, 1/4, 1/8, the next will be 1/16, then 1/32, and then 1/64. So the formula for this is Gn equals 1 over 2 to the n. All right? So it's 1/2 to the n. So if we look here, we see that the shaded part is representing the series. It's saying, okay, so at the very beginning, my first term just takes up half of this square. So this square is 1 unit by 1 unit. So the first term just takes up 1/2. Now, when I put in the next term, it's a quarter. So I'm going to take up this part right here, which is drawn right over here. So now, altogether, I'm at 3/4. And now over here, if I add an eighth, all together, let's see here. So if we put everything in eighths, this is 4/8 plus 2/8 is 6/8 plus 1/8 is 7/8. And what you notice is if we keep doing this, if we take another, if we take our next one, 1/16, it's going to fill in this little area right here. And then 1/32 is going to fill in this area right here. And then 1/64 is going to fill in this area right here. And what we notice is no matter how far we go, we are never going to spill out of the square. We're always going to be confined by this finite area, which is really interesting because we're adding an infinite number of things together. So if what we were talking about with the arithmetic series, if we expect these to always diverge, then this would have to spill out of the square at some point. But if you keep doing a half of each of the blank areas, I mean, you're never going to completely fill in this square. You're going to get to some really, really small values here. In fact, at this point, you can't even see the hole anymore. But if we keep doing half, there will always be space left to fill in, and we'll always have a little bit of space left. So I think I have something at the bottom here. Yeah. So we have this whole geometric idea here of 1 over 2 to the n. If we take this as it goes to infinity, as n goes to infinity of this guy, we're limited. We're limited by this square that has an area of 1 unit by 1 unit, which is 1. So that actually proves, it's kind of an interesting pictorial proof here, that if you keep going to infinity, this sum actually is limited by 1. And so the convention is we say that that limit is equal to 1, or that this sum, if you add up those numbers infinitely, they actually do equal 1, which is kind of cool. So, as with sequences, if the limit as n approaches infinity of Sn exists, because we said S1, S2, S3, we said that these actually create a sequence. So if, as we go to infinity, if it exists, the series is called convergent. So this would certainly be a convergent series because it converges to 1. If the limit does not exist, we call it divergent. So convergent and divergent. So before I move on here, I want to talk about a couple other kind of classic examples, and this is just kind of some Fransky bonus material here, that they talk about dealing with limits and saying that a geometric infinite series actually can add up to a finite number, which is kind of cool. And one of my favorite is that, let's say that you drop, the typical example is a rock, but a ball, doesn't really matter what you're talking about. So let's say that you have a floor here and you drop a ball. So that ball, at some point on its journey down to the floor, must reach a halfway point, right? I mean, at some point it has to be halfway down, and then at some point it has to be another half of that distance. So that'd be at 3/4 of the way down altogether. Then it eventually would have to be half of the way to the floor from that point, and then half of the way to the floor from that point, and half the way to the floor from that point. And so a doubter might say, well, okay, the ball is never going to hit the floor. Well, that doubter has obviously never heard of gravity because it's going to hit the floor. So the way I think about it is if you add up that first half plus the next fourth plus the next 1/8 it'll be, and then it's 1/16, and then it's 1/32, and then 1/64. If you add up all of those distances, it has to equal the entire distance, which is 1, all the way to the floor, because the ball hits the ground. So physically, you can kind of think about this in terms of that. The other one that I actually learned when I was learning this limit the first time was my teacher said, okay, if I walk half the distance to the door, and then I walk half the distance to the door again, and half the distance to the door again, and it's not that he's stopping. He's saying my goal is to walk through the door. I must walk halfway at some point, then I must walk 3/4 of the way, and then 7/8 of the way, and then 15/16 of the way, and then 31/32 of the way, but eventually I go through the door. So it must be that all those limits add up to the entire distance to the door. So if you're still wrestling with how can I add up these things together, hopefully that helps you a little bit. If it doesn't, you guys are going to have to accept it for now, and hopefully between pre-calc and calculus, you'll be able to kind of wrestle with the idea that you can add up these numbers infinitely many times, and you're going to end up with a limit. So, which series converge? Well, what we want to think about here is that we have our formula for a finite geometric series. So we said arithmetic series are hopeless. We can't do those at all unless we have that really weird one where they all equal 0. But in this case, we want to look at just the geometric series. So we're looking at these series, and we want to see which ones are going to converge and which ones are not going to converge. Well, let's see what happens when we take the limit as n goes to infinity of this thing. So the limit as n goes to infinity, we're trying to find s infinity here. So s infinity, what happens when I add these terms all together? So s infinity is going to be the limit as n approaches infinity of Sn, which is the limit as n approaches infinity of this guy right here, which is g1 times 1 minus r to the n, all over 1 minus r. Now notice in here, n is going to infinity, but nothing else is changing. Well, in here, we only see one n. And it's right here. This is the only spot that we have an n in this entire expression. So the g1 is fine, the 1 minus r is fine, those aren't changing. But this n is getting really, really big. So we're taking a number, our ratio, so our common ratio is very important. Our common ratio is very important. And that's because some numbers, when you take them to a very big power, get very big. Other numbers, when you take them to a very big power, get very, very small. So take a second and think what kind of r values we could have here that will actually make this limit exist and converge, and which r values are going to make this diverge and go off to infinity. So take a second to think about that. Alright, so hopefully that you realized here that if we have an r value that is less than 1, if we have an r value that's less than 1, if r is less than 1, like let's say it's, I don't know, 1/3. If I take 1/3 to very big powers, this is going to get smaller and smaller and smaller. So 1/3 times 1/3 is 1/9, then 1/27, then 1 over 81, and then 1 over 243. These numbers are getting very small very quickly. And when n goes to infinity, if r is less than 1, so any number less than 1, doesn't have to be 1/3, it could be 1/2 or 3/4 or 5/6, doesn't matter, anything less than 1, then r to the n goes to 0. R to the n goes to 0 as n goes to infinity. That's important because that means if r is less than 1, this r to the n power here is insignificant. It just turns into 0. So then what does this turn into? This turns into just g1 over 1 minus r. How easy is that formula? It's like the easiest formula I've ever seen. So this is what s infinity is. S infinity for a geometric series, as long as r is less than 1, is just g1 over 1 minus r. So let's be a little bit more specific about this r value. What it really is that if the absolute value of r is less than 1, then this is going to be true. So this is if absolute value of r is less than 1. What that means is we could have negative values too. We could have like negative, I don't know, 2/5 could be our r value. All that means is that we have positive and negative values, but this is still going to get very small. It's going to turn into 0 as n goes to infinity because these numbers are getting smaller and smaller. Yes, it'll be alternating up and down, but it's still going to level off at a value. So if we have a number, this means that r has to be between -1 and 1. If r is between -1 and 1, then we are going to converge. Now this also means that if r is bigger than 1, if r, absolute r we can even say, is bigger than 1, that means if r is greater than 1, or r is less than negative 1, less than or equal to, excuse me, we can put an equal to sign here, because if r is 1, that means that we have the same term over and over again. We have g1, g1, g1. If you add all those together, you're just going to diverge. So if absolute r is greater than or equal to 1, then it diverges. Okay. But this is like the coolest formula ever. If absolute r is less than 1, the infinite series is g1 over 1 minus r. It's such an easy formula. It's one of the most beautiful concepts in math, I think. So let's see what the book has to say about that. This is the same formula. So if you didn't get it on the last slide, you can get it right here. So if we have an infinite geometric series, Sn, where we have g1 times r squared, all the way up to infinity. We keep adding those together as long as g1 is not 0. If g1 is 0, then we're all 0. It's not very interesting. If we have r between negative 1 and 1, another way of saying that is absolute r is less than 1, then it converges. And the limit is g1 over 1 minus r, which we just proved. If r is bigger than 1 or r is less than negative 1, we can just say that that is absolute r is greater than or equal to 1. They actually have strictly greater and strictly less here, but if it's equal to 1, you're also in bad shape. So we can actually add equal signs to these. Then that's where we're going to be divergent. All right. So this is our last formula, and hopefully it's still over on the sideboard. Hopefully no one's erased that. But that will stay up once again for your quiz and for your test, so it's useful. All right, let's try some examples. So I left the formula right here, since you have it on the sideboard anyway. So for this case, what they want us to do is they say, which of the following could be a convergent geometric series? So we're just saying here, which one of these is a series that converges? And we're just looking here for that condition. We want that absolute value of r to be less than 1. So let's see what we have here. For those that could be, they actually want us to calculate it and find the limit. So this first one here, it's actually not even a series. So we don't have to do anything. It's not a series. How do we know that's not a series? Well, they're not adding the terms together. It's just a sequence. So this is not a geometric series at all because it's a sequence. We notice that there actually is a common ratio. It's multiplying by 1/3 every time, but it's not a series. The next one is the same sequence, but they're actually adding them together. So this is a series. So let's see what we have here. We have g1 is 5/3. And let's look at our common ratio. Now you could grab a calculator and do the second term divided by the first term to find that common ratio. But it looks like the 5 stays the top on the same. The 5 stays on the top for all of them. And then we're multiplying by 3 on the bottom. So our ratio is just 1/3. Hey, that's kind of cool. That is less than 1. So we can find our infinite geometric sum. If you added these all the way up to infinity, S infinity is just going to be g1, which is 5/3. Over 1 minus r, which is 1 minus 1/3. That's 5/3 over 2/3. So we can multiply by the reciprocal. Those 3's are going to cancel, and we just end up with 5/2. Little fraction magic there. So if you added all of these up to infinity, you would get 5/2. It's kind of a cool little formula there. Now this next one, let's see what's going on. Once again, it's a series because we're adding numbers together. And it looks like if we divide 160 by 640, or 40 by 160, or 10 by 40, it looks like we have a common ratio of 1/4. And our first term here, g1, is 640. I'll write that down here. Sorry, I'll run out of room there. So we can find our limit because we see that our common ratio here is 1/4, which is less than 1. So S infinity is just going to be our first term, 640. Divided by 1 minus our ratio, which is 1/4. So that's 640 over 3/4. We can multiply by the reciprocal, so it's 640 times 4 over 3. And I calculated that earlier. Let's see what I got. Looks like I got 2560 over 3. 2560 over 3. Which, if you wanted to change that to a decimal, is 853.3 repeated. Cool. So let's look at this last one. So the 2 on the bottom is staying the same. It looks like we're just adding 4 each time on the top. So this is actually an arithmetic series. We're adding 4/2 every time. In fact, we're adding 2. So this is an arithmetic with a constant difference of 4/2. And we said that if we have an arithmetic series, it's always going to diverge. So that one's always going to diverge. All right. So in that case, we will not have a limit. It'll keep adding up to infinity. All right, just one more example here. Hope you're bearing with me. These are so nice because this formula is just so simple. So here they want us to find a fraction for this infinitely repeating decimal. Infinite seems like something we've been talking a lot about today, so let's see if we can make it work. So they say the 65 repeats forever. 65, 65, 65, 65. So the first thing I'm going to do here is just chop off the 39.4. So this is equal to 39.4 plus, let's see what we have left. So the next part of that is going to be 0.065. And then we could add to that 0.00065, because this takes up those two places right there. And then we have the next 65. And then the next one will be 0.12345 zeros 65. And that's going to keep adding together. Well, so this part is kind of taken care of, the 39.4, but the rest of it here looks like it might make a geometric series. So 0.65, that's our first term. G1 is 0.065. Now to find the constant ratio, you could take the second term and divide it by the first, or the third term and divide by the second. But it looks like we just keep moving that 65 over two decimal places. So that means that our constant ratio is just 0.01. Or you could write it as 1 over 100. Either way will work. So now we have a constant ratio, we have our first term, and that constant ratio is certainly less than 1, so we can use our formula. So this sum altogether is going to be G1, which is 0.065, divided by 1 minus 0.01. That is 0.065 over 0.99. If we move everything over a few decimal places, that's 65 over 990. Because they're asking for a fraction here, so we better keep things in fractions. I want a simple fraction for that. So we have our fraction for this infinite geometric series here on the right, and we have our 39.4 on the left. Well, 39.4, that is 394 over 10. So what I would do is add these two fractions. So we have 394 over 10 plus 65 over 990. Well, we need a common denominator. It's kind of annoying, so we're going to multiply by 99 on the top and bottom here. And we end up, after we get our common denominator and add across the top, this ends up being 39,071 divided by 990. I think that's kind of cool. You can do this with any repeating decimal. You do this with any repeating decimal, it creates a geometric series, and you're able to find the fraction that's equal to that sum. It's kind of cool. Alright, that's all I've got for infinite geometric series here. And what I want you to do tonight, or over the weekend if you're going to the hockey game, is try the Chapter 5 self-test. You should be able to do everything except number 11. That's a problem from 8.6, so don't bother with that one. But everything else you should be able to do. Now this is important. If you're going to the hockey game tomorrow, make sure you look at the review materials. The video is online already, so go ahead and take a look at that. And all it really is, the video is just showing how to do a couple problems from the review sheets. So give them a shot. Look at the video if you kind of need a little nudge in the right direction. And be ready for the quiz on Monday. I am asking, if you're here Wednesday, you should be watching this video on Wednesday, I am expecting you guys to take the quiz on Monday. So I'm asking the sub to take careful attendance today, and you should be able to take the quiz on Monday, because tomorrow is just a review day. The reason I scheduled it that way is because I knew the hockey game was coming up. So enjoy the hockey game, have fun there, but do make sure you take a look at the review materials, try the sheets in the packet, and you should be all set for the quiz on Monday. Remember, the formulas will be up on the board, so you guys should do just fine. All right, I love you guys. That's why I'm here. Have a great day.